in these times. Yeah, so I'll talk about optimization of mean field spin glass Hamiltonians. And this is joint work with Andrea Montanari and Mark Sellke, who's a graduate student in mathematics at Stanford. Oh, all right. All right, so I guess the high level motivation is to optimize non-convex and combinatorial functions in polynomial time. So of course, this is not always possible in the worst case, but we may hope that there are certain nice distributional assumptions that we can put on our problem so that this problem becomes easy. And the same thing goes for sampling for high dimensional distribution. So, I mean, you can imagine all sorts of applications in which these kind of paradigms show up, and these kind of needs, these ideas or problems will show up, and you need to solve them, right? And in this talk, I will just consider a very simple model from theoretical physics, which exhibits a very nice structure, very extremely rich structure that we can take advantage of in order to solve these problems in that special case. So let me define the models that I will be talking about for the rest of the talk. And this model is called the mixed p-spin Hamiltonian, or the Ising mixed p-spin Hamiltonian. So formally, you can just consider that you're on the hypercube sigma n plus minus 1 to the power n, and you can put on that space a Gaussian process centered, and it has a covariance that only depends on the inner products between the points in which you evaluate it, right? And this non-linearity just defines the model Xi. And you can otherwise define this pointwise, this random variable, you can define it pointwise with this expression. And so here you have a series of sums of inner products between tensors of order P, and each the coefficients here, the W's are random and they're Gaussian. So you have W is a symmetric Gaussian tensor. And these CPs are just coefficients that define the model, right? So if you try to compute the covariance here, you can define it alternatively by just letting C to be this a power series of this corresponding to the coefficients CP, right? And two examples to keep in mind is just one, which is the quadratic case, which is the two-spin or the Schrödinger-Kirkpatrick model, where you just have a sum of two-body interactions, Jij, sigma I, sigma j. And here you can just compute the covariance, so you will get that Xi is just x squared or x squared over 2. The other case is the three-spin model, which is just the same thing, but for three wise interactions, and the model looks like this, and Xi will be just x cubed. And the main problem here that I'll be talking about is to maximize this Hamiltonian subject to the configuration being binary. So you're still on the hypercube and would like to get a maximal value of this Hamiltonian, right? So this is called the ground state. So just as a matter of sign convention, the ground state typically is the lowest energy here, because the distribution of the Hamiltonian is symmetric by a sign flip. So I'm just looking at maximization, but it's strictly the same thing if you want to minimize. So you want to do it efficiently, right? What do I mean by efficiently? So here I'll just assume that I have access to a gradient oracle. I can just query for a point that asks an oracle to compute the gradient for me at that point, and he'll return the answer. And I want to produce a configuration sigma that depends on all the queries that I've done, such that I'm pretty good in terms of value. So I'm at least 1 minus epsilon optimal. And I want the number of the queries to be polynomial in n and 1 over epsilon. So that's the desiderata. So this is, of course, NP hard in the worst case. And even for quadratic, before considering more general functions, you can see that for quadratic, this is NP hard for a very bad approximation already. If you're just looking at an approximation ratio that is 1 over log n to some power, then that's already NP hard. But here, since the model is random, so we can try to exploit the randomness and circumvent this worst case scenario. So let me talk maybe one approach that one can naturally think about is convex relaxation. So let me just restrict the discussion to the quadratic case. So I just have a Schrödinger-Kirkpatrick model. So this is the model that this is the optimization problem that I'm trying to solve. And for reasons that will become clear, I'll just explain this. This turns out to be, you can numerically evaluate this, and it's 1.52. Okay, that's the Parisi formula for the model. And so one spectral relaxation that you can do is, the first one is the spectral one, which is you can just remove the constraint that the sigma is binary and just replace it by a norm constraint. And so the norm of a vector here is square root n, then you can just put that in the constraints, right? So that's just the first eigenvalue of your matrix, G, which is 2, right? So you have a gap here. The next thing you can try to do is relax in a stronger way and look at a semi-definite programming relaxation. And here, so what you can do is you just, this is just the inner product between G and sigma sigma transpose. You can replace sigma sigma transpose by a symmetric matrix CSD X, and the diagonal will be the identity because that's the constraint that corresponds to the hypercube. Sigma I squared is 1, right? And you can try to compute this, and there is an analysis that has been done by Andrea and Subabrata-Sen, and that still is 2, so you don't improve over the spectral algorithm. Turns out that it's okay, so you can try to systematically try to improve this better and better, and then you can look at degree 4 SOS relaxation. It turns out that this is actually also 2. This is a result by Tim Kuniski and Afonso. Okay, so there is evidence, at least in this line of work, there is an evidence that the spectral bound, which is 2, it's the best computationally possible. But what does that mean? So it turns out that this is best possible for certification. So what does that mean? So here we're actually trying to solve a problem that is a bit harder than the original one that we started with. We're relaxing so that the value that we get is always no smaller, it's always larger than or equal. And that turns out to be true regardless of the distribution of this matrix G, right? So it doesn't have to be Gaussian, but just because it's a convex relaxation. And you want furthermore that for G that is Gaussian or GOE, you want the value of your relaxation to be as close as possible to the ground state, to the optimal thing. And that turns out to be too much. So for this particular problem, which computer scientists call certification, then there is evidence that this is the best possible. The spectral bound, which is 2, is the best possible in polynomial time. So you can try to look at now, you can generalize this approach to problems that are not quadratic. So if you look at a K-spin model, pure K-spin model, where there is just the term that corresponds to the number K appears in the series. And you can relax the binary constraints to a spherical one. And you can try to solve the level K sum of squares relaxation for this problem and try to analyze its performance. Turns out that it's bigger than the optimal value of the ground state by a factor that depends on n polynomially. So this is even worse than the case K equals 2. So an approach that is quite different is the Glauber dynamics. And there's a rich literature here. And so what is known so far is that there is slow mixing. So you only mix in exponential time, or you hit a set of good value in exponential time. And typically for short times, you will get stuck at a value that is called the threshold energy, which is known for the spherical case, but there's a formula for it for the spherical case. And for the binary case, we know the value, but theoretically there is no closed form formula. So that's the state of the art for this type of algorithm. So there's another approach, which I call here dual algorithms for a reason that will become clear. So for the spherical model here, I mean, just you remove the constraints of the hypercube and you put the sphere of the same radius. There's an algorithm that was proposed by Ilian Subag, that actually achieves the best, the ground state. So, so the generalization of that algorithm was proposed by Andrea for the Ising SK model. And both of these algorithms will achieve an approximate global optimum under a certain condition that is called the no overlap gap assumption. And so I'll explain what this is a bit later, but just to let you know, so for a problem that does not exhibit an overlap gap, these algorithms will work certifiably, provably, but it turns out that also this condition is in a certain sense necessary and sufficient, because if there is overlap gap, then there's a lot of work from David Gamarnik and its co-authors, in particular for the problem that we care about. These are the relevant references. They show that for a certain class of algorithms, then if there is overlap gap, then you cannot achieve the ground state. So this condition is in some sense necessary and sufficient. Okay, so let me tell you now the details of the results. So if you want to optimize this model, you'd better know what you're shooting for, because this is not a convex problem. You don't have a checkable optimality condition that you can just check. So you'd better know the value that you're trying to shoot for. And this is called the Parisi formula for the ground states. And let me explain it. So here you have to start with a set. So let U be a set of functions that go from the interval 0, 1 to the positive reals. These are non-decreasing and they're L1. You have to consider this nonlinear PDE that is called the Parisi PDE, in which you take one of these guys and put it here in the nonlinearity. You solve this PDE backwards from this terminal condition, right? And now you consider this functional that just takes the solution at the point 0, 0 and subtracts this linear term in gamma. So this is a functional of gamma that is called the Parisi functional. And the theorem here is that the maximum, so the ground state, the maximum of the Hamiltonian over the hypercube divided by n will converge as n goes to infinity to the infimum of this functional over the class U. Okay, so this is in my opinion, this is a crowning jewel of this whole area of spin glass theory, an exact characterization in the limits of the maximal energy of the ground state energy in terms of a variational principle that doesn't depend on n. So the first thing you would think here is, how are these two related? They seem to be very different objects. How does this characterization in terms of nonlinear PDEs and variational problems show up from this discrete problem? So that's one of the questions that we'll try to shed light on a bit later in the talk. The second one is, of course, here you're trying to maximize. And when you compute the limits in terms of this Parisi PDE, you see this infimum. So you're trying to take an infimum over a functional. So how does this maximum turns into an infimum? This seems to be a mystery so far. So just a small word about the landscape of this Hamiltonian. So if you look at the superlevel sets of this Hamiltonian, which means the configurations sigma that are at least 1 minus epsilon optimal. And so look at this set and sample two guys independent samples copies from it, sigma 1 and sigma 2, from the uniform measure on this set. Then it turns out that the inner product between these two samples will converge to a non-degenerate random variable. So you wouldn't have concentration at all. So if you think of a convex function, then these superlevel sets will be convex because the function is, or concave function because we're maximizing. These superlevel sets will be convex for all values of epsilon. And now if you take two samples from a convex set in high dimension, that their inner product has to concentrate. This is by convexity. This is by the Brun-Minkowski theorem, right? So the fact that this random variable doesn't converge to anything deterministic just is another measure of how far from convex this problem is. So it's very rough. The landscape is extremely rough. So related to this, so if you want to understand the structure of this problem, there's this idea that is key to this kind of space of spin glass literature, which is the ultrametric structure. So behind this maximum, there is an organization of states that is hierarchical, and it is represented by a tree. It has a root, and then it branches infinitely often. And you can parameterize it by time. So here I'm just depicting a picture that is discrete, but you can actually, in the limits, this is actually a continuum tree in a certain sense. So what does this mean? So here you can look at the clusters of optima or near optima in the cube and the hypercube, and these will be represented by the leaves of this tree. And so if you look at the internal nodes in this tree that are called also ancestor nodes, these are associated to actual physical points in the solid cube -1, 1. Okay. And at level t, if I'm at level t and I look at an ancestor state at a level t, that will correspond to a point m that furthermore has a norm, an L2 norm that is about t when you normalize it properly. Okay. So these are spheres that are concentrics and that grow as t evolves. And at 1, of course, when you look at a point that has L2 norm 1 divided by n, then that will have to be on the extreme points of the hypercube. That's just ±1, which is consistent with this, the first bullet. Moreover, the Euclidean distance between two clusters or two near optima is reflected by the distance in the tree. So you have a hierarchical organization. If you look at a point here and a point here, for instance, then their Euclidean distance is represented by the distance in the tree, like this. So this comes from a groundbreaking paper that came in 1985 and is called The Microstructure of Ultrametricity. And that explains in detail way more than what I just described to you, what should happen in principle. And in that paper, they had foresight, an amazing foresight that I just became aware of this quote. So they say in the paper that the ultrametric topology of the space of equilibrium states of a spin glass deserves special attention. Such an organization might exist in other systems with frustration and disorder, and it should have consequences in such fields such as optimization and neural networks. So this was written in '85, and it hasn't been exploited, I guess, until now. So until the papers of Subag and Andrea and then ours. So the algorithmic idea is really to exploit this structure. And so the high-level idea is to start from the root of this tree and to construct a path, a random path that just explores this tree, and at some point it arrives at a leaf, and the leaf will be, by the description that I showed you, an optimum point. So there's a geometric picture as well, which corresponds, which is just the mirror of this abstract idea of a tree. You start from the origin of the cube, or the origin of Rn, and then you start to build a stochastic path that will at some point be converge to one of the extreme points of the cube. And this path will be controlled in a certain way. It's a controlled diffusion, and I'll show you how it is controlled. So the main result is the following. So there exists an algorithm which outputs a configuration sigma. So the number of iterations of the number of the length of the conversation with the oracle is actually independent of n. It only uniquely depends on epsilon. So you have epsilon iterations, such that you're at least 1 minus epsilon times a certain value that is almost the Parisi formula. But here we're optimizing over a slightly larger space L instead of optimizing over the space of monotone functions U, which would be the ground state energy. We're optimizing over a slightly bigger space that I call L, and this space contains non-monotone functions, so they don't have all to be non-decreasing. There is a 1 over n that should show up here for normalization. Okay. So of course, this is optimal if this infimum over this larger space is actually also equal to the infimum over the smaller space U, right? And this would be the ground state energy. And if, in particular, if this infimum is achieved at a non-decreasing function, right? I just repeated what I just said, right? So that would be a sufficient condition for optimality. In particular, if the infimum over the space of monotone functions U, this characterizes the ground state energy, is achieved at a strictly increasing function, then just because of convexity of the Parisi functional, then this would also, the infimum over this larger space would also be achieved at this exact same gamma, which is strictly increasing, and therefore you would have optimality, right? So this is the condition of no overlap gap. So at least at 0 temperature, we're going to say that the model has no overlap gap. If when you look at the infimum over all gammas that are in this space U of non-decreasing functions, then the optimum is achieved at a strictly increasing function, okay? This is also in physics called the continuous or full replica symmetry breaking. So just looking at lower bounds that I referred to earlier by David and co-authors, they consider, or they use a slightly stronger and non-asymptotic version of the statement at positive temperature. And these two notions should be somehow related, at least morally, because they should describe the same thing, but mathematically, this is not the case yet, at least at 0 temperature. And by the way, please just interrupt me if you want to ask any questions. Furthermore, so in addition to this achievability results, this is actually the best value that is algorithmically possible. So we can also show that no IMP algorithm of a certain smaller class than just the general class of IMP algorithm, no such algorithm can achieve a value that is larger than what this particular algorithm achieves, okay? So this seems to indicate that there is an algorithmic threshold for optimization in spin glasses. So, okay, so we did some simulations. So in particular for the 2-spin SK, so we can solve these variational problems by discretizing them. And you can try to compute the optimal gamma. And this optimal gamma is indeed strictly increasing for the Schoentinker quadratic model. And you can compute the value, and the ground state is 0.76. And this is related to the value that I showed you in the convex relaxation section of the talk. That would be just twice this value because of normalization. And so we see here, at least numerically, that gamma is strictly increasing. So the model doesn't have an overlap gap. Therefore, the algorithm should be optimal. And indeed, you can check that it is optimal by simulation. But just proving that there is an overlap gap mathematically, that's one of the big open problems in mathematical physics in this area currently. Now you can look at the 3-spin model, which is the 3-body interaction. And then the problem is very different here. So if you optimize over the space of non-decreasing functions, this is what you get. So then the function will be constant up to a certain point and then start to diverge. On the other hand, if you remove the non-decreasing constraints, then it's very far from being non-decreasing. So it will go down and at some point and go up again. So this is a very non-decreasing function as you can imagine. So the algorithmic value here that the algorithm achieves is about 0.8, about that. And the ground state is about 0.81. So it's slightly larger than that. So there is a gap between what we can achieve and the ground state. So we can compare this also to what's called the threshold energy. And the threshold energy, again, I can remind you, is the energy that is achieved by Langevin type dynamics in short time. So those get stuck at a strictly smaller value, which is 0.78. So there is a gap between that threshold energy and what our algorithm can achieve. So it seems that our algorithm can do strictly better than Langevin type dynamics or Glauber type dynamics. And this wasn't known before. So there wasn't, until now, there wasn't an algorithm that was able to achieve a strictly stronger, bigger value than Langevin type dynamics. So this is an example of that. So the algorithm belongs to this very large class of approximate message passing algorithm that I will try to describe. So ask me a question. Maybe this is a good time to pause. Go ahead.
Yeah, maybe actually it's a good time to pause. And I would like to ask you something. So are you going to define this class L? Like you say that it contains non-monotone functions, but like, are you going to say what it is?
So I don't have a slide for it, but I can tell you what it is. It's a class, it's technically defined. There are a bunch of technicalities that are involved in the definition, but it's a class of functions that have finite total variation up to on any interval of the form 0t, okay? For t strictly smaller than 1. And what else? What do I need more? And they should be L1. They should be L1, and they should have the finite total variation from for any interval of the form 0t, for t strictly smaller than 1. But then you allow them to diverge at the end.
I guess the question is, if there is an increasing gamma in this class, does it fall into U necessarily, or it could be?
Yeah. No. So that's a good remark. So if you intersect this class with the set of non-decreasing functions, that is U.
Okay, good.
That is equal to U. Thank you. That's a good detail that I skipped. Yeah.
Okay, thank you.
So if there are no other questions, I'll move on to the description of the algorithm. Okay. So there's a general class that is called approximate message passing algorithms, and it is in its most generality, I can describe it as follows. So you can start with a certain initialization. So what you do is you choose any function FL that depends on the entire history of the algorithm up to that point, and call it M. Then compute the gradients at that point M, and then the oracle will return this value for you. And then subtract a linear combination of the previous points with a certain coefficient D that have a closed form expression that you can write down. These are no problem. And that will give you the next iterate, the L+1. So this defines a class of algorithms given a choice of functions FL. And in particular, this function, so I showed you here, this function doesn't have to be constant, it can change from iteration to the next, not a problem. Okay. So there's a general characterization of all of these algorithms, says that in the limit, as n goes to infinity, in a certain sense, these iterates up to any fixed time L, they will converge to a certain centered Gaussian vector. So it's centered, it's Gaussian, and its covariance is given recursively by this formula. So it's psi prime. So that at the next step, when you add 1 to the iterates here, it'll just be the psi prime of the expectation of FL times FL prime. Okay. So here, by designing these functions f, you can just give a covariance, whatever covariance you want to this Gaussian process. So this gives you a huge amount of choice. It gives you a lot of freedom in designing whatever Gaussian process you would like out of this algorithm. So let me just give you an example. For the quadratic case, then psi prime of x is x, okay? And the algorithm will look like this because the gradient of this function is just g over square root n. And this looks probably like the iteration that you've seen earlier, maybe in previous in earlier literature. And here, so as I said, psi prime of x is x, then it's just the state evolution iteration just boils down to this last equation here. Okay. I'll further simplify this, and I'll just assume here that f doesn't depend on all of the past, it only depends on the last iterate, which is ZL, and f also doesn't change with the iterations, with the iteration count. Okay. Then turns out that the sum here will just boil down to only one term, which is this one, and this BL can be computed explicitly, and this is its expression. So maybe this is one of the first AMP algorithm that was devised, right? Maybe by Walthausen, and more generally maybe by in the tap equations, if you know what that is. So coordinate-wise, so this is just one remark here. So this is a vector of size n, and this function actually is from the reals to the reals. But what I mean by f of ZL is just f applied to every coordinate independently. That's what I mean by f of ZL. And so coordinate-wise, this will look like this. The iteration will look like that. Okay, so this memory term here, so this looks like some kind of power iteration, but there is a memory term here, and it has a very important function. So the role of this memory term is to replace G by a new copy at every iteration, essentially. So if you didn't put that term in the iteration, then this ML will depend on the G, on the randomness of G, because that's how you computed it in previous iterations, right? So these two terms won't be independent. But the role of this memory term is just to act as if these terms are independent, just subtracts the right amount of dependence so that these two at every iteration will act as if they were independent. So let's just assume that this term wasn't there and you replace G by a new independent copy. Then if you look at the inner products between Z at two stages of the algorithm, L and J, that given that ansatz, then that would be this, where G is just independent of ML and MJ. And just by concentration of measure, that would be just the inner product of ML and MJ, right? So that's what state evolution says. Just Z at these two times will be just ML, MJ, and M being F, right? So let's see, I was planning to give a small sketch of how this proof works of state evolution. So I think I still have time to do it. So let's do it. So at iteration 1, this is what the iteration looks like, right? Now I'm initializing m-1 to be 0. So that's just this term. And Zj are fixed. So that's how I initialize them. So this is a deterministic term, and these are Gaussian. So this is just a Gaussian random variable. So the first iteration is trivial. Now let's look at the second iteration. So here, this is Zi1 is just written here. Now Zi2 is the same iteration, again, for AMP, but this is not 0 now. So I'm going to replace J1 by its expression inside F. This is what it looks like. Okay. Now there is dependence because this term will depend. It has a certain dependence with the GIJs that are outside. So let's try to disentangle it. So I just here in this inner sum, I just isolated the term k equals I. So here it is, that's the term k equals I. Now this term is independent of what's going on here. That's the first observation. The second observation is that this term is small, is of order 1 over square root n, so you can do a Taylor expansion. Okay. So let's do a Taylor expansion. So here, this term that is in maybe pink or orange is this one. It's what I call J to I. And then if you Taylor expand with respect to this, then you get a term that depends on F prime, right? And this Ji will just combine with these guys. Since the matrix is symmetric, that will give you a square. And this sum is over J, it doesn't depend on I, right? So now you can just match these two guys, right? And in particular, so here, this is a random term, but it will concentrate in the GI just because, again, this guy, this J, Zj to I is independent from these Gaussian Jijs. This term will concentrate around just the average of these F primes, which is almost this, D. Now you just have to put back the term that corresponds to K equals I again in order for this Z1 to just become this Z. And that will just incur a very small error that you can neglect asymptotically. Now these two terms will just balance each other. So the presence of this memory term will just kill this term, right? So then you obtain this term, sorry. You just obtain this term. Now again, by the same observation, these two guys are independent. So this is just Gaussian. Okay? So now that was just for the second iteration, but you would have to be able to do this for every iteration. But then the path of dependence between the random variables would get longer and longer. And in particular, this approach is very difficult to make rigorous. But there is a way to make it rigorous if these coefficients are indeed Gaussian, and that's called what Bolthausen came up with. It's called the Gaussian conditioning technique. And it has been adapted and ameliorated by several authors later. And if these coefficients are not Gaussian, but there's, let's say, plus minus 1, for instance, then we expect universality in the sense that this algorithm should behave as if the disorder was Gaussian, and that's indeed true. And that's what was proved in a certain case by Montanari and in a more general setting by very recently in a beautiful paper by Chen and Lam. Okay. Now back to optimization. So I just showed you an algorithm. Doesn't have anything to do with our problem originally. This is just a very generic iteration that you can apply to anything you would like, and it doesn't have necessarily to be related to this specific Parisi type problem. So that's just an interesting iteration in its own right. Now let's go back to the choice, to the algorithm, to the specific task at hand. And in particular, I just showed you that we have this algorithm that depends on these FLs, and you would like to choose them nicely. You would like to choose them appropriately so that you do something non-trivial. So it turns out that space is really large to optimize over. So we're going to try to reduce it by just making further assumptions. And in particular, the key assumption here that we're going to make, or the key the algorithmic design choice that we're going to make, is this idea of orthogonal updates that originates from Subag, from the paper of Subag in the spherical case. And the idea, just simply put, is that you have at every iteration of the algorithm is incremental, and at every iteration, the next increment that is put by the algorithm is orthogonal to all the previous ones. Okay. So now if you put this constraint into the choice, if you impose this constraint into the class of FLs, then this drastically actually reduces the complexity of that class. And now you can optimize over it. So let's see why. So if you assume this, then just by state evolution, since the Z's and the M's have the same covariance structure, then it will also mean that the increments in Z's will be orthogonal to the Zij's up to J equals L, or smaller than L, right? By the way, these orthogonality conditions here are approximate, of course. They hold in the limits. Okay, so now we have a Gaussian process, right? And that has orthogonal increments. Now, the first thing that will jump into your mind when I tell you that you have a centered Gaussian process that has orthogonal increments is Brownian motion. So what we can do, we can just force Z to be Brownian motion by a choice of these functions FL, okay? Brownian motion sampled at discrete times since the algorithm evolves at discrete steps. So the ansatz that I put is I'm going to start my iteration with a Gaussian that has a small variance, delta, and delta will be the step size, basically the discretization of time, and I'm going to let delta go to 0 at the end. Now my ML, since I want to enforce this orthogonality constraints, will be just a sum of increments in the z's. And these increments are multiplied by a term uj that depends only on the first j iterates. So you just have a predictable sequence that depends on the past up to that point. And you're just summing all of these increments, okay? And these u's are now my control. So I have to choose wisely these u's. So I've reduced the choice of the s into a choice of the u's, okay? So this somehow doesn't seem much, but now it's enough. Now this class is small enough so that we can optimize over it and get the best, characterize the best UJs. Okay, so these will be my controls. And of course, you can see that if these increments are independent, then the M's will satisfy this constraint. Does this make sense? This is the main idea, actually. Okay. Now, there is a certain condition that you would have to put on these U's so that you get orthogonality of the M. So let's see what that condition is. We're going to just try to see what happens when you try to enforce this. So let's assume that the Z's, now I switch to capital Z's because here I'm talking about the limits, the infinite limits, N goes to infinity. But you can just think of these as being the original Z's, whatever. So if you assume that you have a sequence up to time L that has independent increments. So these are Gaussian centered, that they have independent increments and the increments have variance delta. Okay, so up to time L. Now you want to show that the next increment that you make in the algorithm will still verify this property. So we want to show that this increment is orthogonal to the previous one, to the previous instances, Zj. And you want to show that that increment has variance delta. So this is an inductive argument. Turns out that this is a very simple, and you can just do it as an exercise actually, just use state evolution to show that a necessary condition for this statement to happen, given the first one, is that the second moment of the UJs would be 1 at every time J. So this is a constraint that has to be satisfied for the algorithm to work. Okay, fine. Let's just put that as a constraint. The next thing you would need to do is try to understand what is the value that is achieved by these iterates up to a certain time L. So here I'm taking L to be delta inverse. And what you can show with a simple a certain computation is that in the limit n goes to infinity followed by delta to 0, this energy that you will achieve is given by this variational, by this integral, sorry, by the expectation of the integral of this ut dt. So ut would be the continuous version of these uj. So these are functions that depend on the past, but in the limit you can just consider these uj's to be a predictable process, a process that is random and that is progressively measurable with respect to the Brownian motion to which these z's converge. Does that make sense? Okay, now the necessary condition that I just showed you is that the second moment of u is 1 at every time. That's just necessary. And I'm going to put another condition that is just very specific to the model that we're studying. It's because we're looking for ±1 configurations. I want M1, which is the integral of this process with respect to the Brownian motion, to be between -1 and 1. So why do I want that? Turns out that this M in the ultrametric description of the level sets of the Hamiltonian that I showed you, so the ultrametric structure, M at time 1 is basically the centroid or the mean, the center of mass of those clusters of near optima. So the law of this M1 is the center of mass of the cluster of near optima. You want it to be between -1 and 1 so that you can at the end just round it to the closest value. It turns out that the optimal one, so if you optimize over these u's, this M1 will be actually either +1 or -1 almost surely, but that will come later. So now you have a value, you have constraints, now you can optimize this value. You want to choose the u's so that this value is as large as possible. Okay, so that gives you a stochastic control problem. So let's call the value of that stochastic control problem E star. Okay. Now I want to solve it. So you can stare at this for a while and try to understand how to solve it. It's not very clear. But one thing that you will figure out after, well, I stared at it for a couple of weeks, and it turns out that this constraint is the most difficult one to deal with. It's a non-convex constraint. So this one is convex. This is a linear functional. This constraint is non-convex. So I'm going to try to dualize it. I'm going to try to relax the problem. Okay. So I'm going to put it in a Lagrange multiplier. So this is the constraint with the expectation. And I'm going to put a Lagrange multiplier that I'm calling mu here. Okay. So I remove the constraint and I put it in the objective function. And so this is the dualized version, or the Lagrangian formulation of the problem. And I'm going to suggestively call this mu to be just the integral from t to 1 of gamma. Okay, so I just did this change of variables. This doesn't seem clear why you would do this now, but that turns out to be the right one in hindsight. Okay, so let's just call this mu to be the minus the integral of gamma. Okay. Now, E star is, of course, no larger than this relaxation, right? Because if you just force the second moment of u to be 1, then this term will vanish. If you put in the expectation, this term will vanish, and that will give you something that is no larger than the supremum. That didn't happen, right? So the main theorem here is that this relaxation that depends on gamma is the Parisi formula. So this thing that is describing the algorithm turns out to be actually the Parisi formula. Okay, at that point gamma for any gamma. Now you have an upper bound on the energy that is achieved by your algorithm that is given by P of gamma, and this upper bound holds for every gamma under certain conditions. Now you can optimize over all of those gamma so that you make this upper bound as tight as possible. Turns out that if you optimize over a large enough space, which in our analysis turns out to be L, then you can make this inequality turn to an equality, and that will give you exactly the value of your algorithm. So this is how you prove that your algorithm achieves a variational principle that is almost the Parisi given by the Parisi variational principle, but it's the class of functions over which you're optimizing is slightly larger. Okay. Are there any questions so far? I'll just, in the next couple of minutes, I'll move on to a sketch of the proof of these two points. So just let me know if there are any questions here. Okay, let's try to understand maybe the high level ideas. In order to prove that this relaxation that is given by the stochastic control problem is the Parisi formula, or the Parisi functional at that point gamma. So let's fix gamma. And I'm going to consider a function that is going to call v gamma of t and z. So depend on time and a variable that I call z. That is a slight modification of this variational problem. So I'm going to just modify it in the following way. I'll start from time t instead of 0. Okay. And in the constraints, so again, I'm going to start in at time t, but I'm adding a z here. So this is a function that you can cook up. Just eyeballing this thing, you can just cook up this function and just consider it. Okay, so this is a function. And of course, if you take t to be 0 and z to be 0, this is exactly the same thing, just by substitution. Now, by understanding this function, I would hope to understand its value at time 0. Okay. Now, I'm going to try to find a formula for this function, or at least try to understand how it behaves. So here it's a stochastic optimal control problem. You have a supremum over processes that are from t to 1. They're adapted with respect to Brownian motion. You can look up books about stochastic control, and you see that dynamic programming is an IDF choice in order to solve this kind of problems. So what you can do is you can split these integrals from t to theta, and then add to theta, from theta to the integral from theta to 1, and split this supremum. Since you have a supremum over all processes from t to 1, you can split it on processes from t to theta and theta to 1. and then push the supremum from theta to 1 inside. Okay, by a Markov property, you can do this. And it turns out that V will satisfy a dynamic programming equation that will look like this. Okay, so you have these two terms from T to theta, but this constraint is absorbed in a new function V that is evaluated at time theta, and then the time parameter is theta, and the space parameter is V plus the integral of this thing from T to theta. Okay. Now I'm gonna let theta to go to T, and I'm gonna divide by theta minus T to get the Hamilton-Jacobi-Bellman equation. So if you take this, at least this is all formal. This is, none of this stuff is rigorous, by the way. This is all formal. You take T to theta, then you have to apply Ito's formula on this term, that where you're gonna get the time derivative and the second derivative that corresponds to the Ito term. And the supremum will just reduce to a supremum over univariate real parameters U that are univariates, and it'll give you a PDE that looks like this. Okay? So now if you look at this PDE, it's non-linear, it looks really horrible. I don't know how to solve it. I'm not even sure that there are any classical solutions to this PDE. But okay, so you can have a little bit of faith, and hopefully its PDE is related to the Parisi PDE, and we can try to maybe invent some clever change of variables that will turn one into the other. But that's what we do. So if you write V in this form, okay, so there is the main, so forget about these two terms, these are just compensation terms. The main thing here is the Legendre transform of a new function that I call suggestively, again, phi of gamma. This is just the Legendre transform of a new function phi of gamma. Now, turns out that this Hamilton-Jacobi-Bellman equation, if you plug in this ansatz, will turn into the Parisi PDE for this function phi. Okay. So this seems to fall out of nowhere, but okay. So there are reasons to expect that the Legendre transform has to play a role here, and indeed it does. So you can show this equivalence. Now this is great. Now we just have to evaluate again. So remember that rel, the relaxation at point gamma, is the value of this function at points at time 0 and space parameter is 0. Now you can just evaluate that. So if you look at this function at time 0 and space 0, right, so you put z to be 0 here, you put z to be 0, this term goes away. Now, if you put the time to be 0 here, that will give you this term. Now, you just have to look at what happens here. So z will go away, and you're just looking at the infimum of phi at time 0 and x. So infimum over x at phi of 0x. If phi turns out actually to be even and convex, so the infimum is achieved at x equals 0, that will give you this formula, which is phi of 0, 0. And that's exactly the Parisi formula, the Parisi functional, which is phi of gamma. So that will finish in modulo many steps, will finish your proof. Okay. Are there any questions on this part? Okay, so perhaps I'd like to conclude. So the main message here is this duality between the Parisi formula and the stochastic control problem. So initially you started with a maximization problem. You're trying to get the maximal energy possible for your Hamiltonian, random Hamiltonian in a hypercube. And you can turn that question. So you apply an algorithm and you turn that question into a stochastic control problem that is also a supremum because you're still trying to maximize an energy. And the Parisi formula turns out to be just the dual in the sense of convex optimization of that supremum. So that's why you get an infimum, is because you've chosen to take the dual of this formula. So maybe in an alternate version of history, if Giorgio Parisi just followed an algorithmic approach in order to solve the SK model, and he would have ended up with a stochastic control problem, which is this one, and this would be called the Parisi formula, not this one. And the question of why the supremum turns into an infimum would have been a non-issue because you just take the dual and that's why you get an infimum. So this hopefully sheds some light on this duality between sup and inf in these spin glass problems. Okay, so let's see. Some interesting directions here is to understand the physical interpretation of this extended Parisi principle. This is just what the algorithm gives. This is not, or at least for now, it's not an intrinsic property or doesn't describe any intrinsic property of the landscape of the Hamiltonian. This is just what the algorithm, gives, right? So we would like to understand if there is a physical interpretation of what the algorithm gives in terms of intrinsic properties of the Hamiltonian. That is not clear. One other thing is to explore this duality property. Hopefully it is very useful just for the sake of proving things that we didn't know how to prove from the original formulation of the Parisi formula. So that would be an interesting thing to study. And of course, there are many other models for which this type of behavior is expected, right? If you look at the perceptron, K-stats, and bipartite problems and Hopfield type models, beyond the Ising mixed p-spin model, the same algorithm or a version of that algorithm can be put to use in order to try to shed light on these questions, at least algorithmically. Now, I talked about optimization. I didn't talk about sampling. So if you look at the problem at positive temperature and you would like, let's say, to produce a sample, an approximate sample from the Gibbs measure, we hope to be able to exploit the same ideas in order to produce samples. But for now, it's not absolutely clear how you should do it because the algorithm is somehow deterministic. And you would have to devise some kind of randomized version of this algorithm in order to include the randomness of the sample in the space. So that's something that is very interesting and that we're very interested in following. And the next frontier here is sparse models. So I talked about fully connected models or dense models at least. When you look at sparse models, for instance, spin systems on random regular graphs, for instance, or sparse Erdős-Renyi graph, by sparse I mean average degree, which is constant, then there is a ultrametric structure that is expected for these type of problems in the same vein as the one that I showed you. But there is no Parisi formula so far for these kind of problems. If I asked you to compute the free energy of an Ising model on a random regular graph with fixed degree, so far there isn't a convincing formulation for the asymptotic value. So we don't know even at the physics level of rigor. So for instance, in computer science, an equivalent question would be to consider a mean bisection or max cuts on random regular graphs and try to understand the value first, and then try to come up with an algorithm to solve these combinatorial problems. Actually, we believe that there is no overlap gap for these problems, whatever that means in the formulation in the limits. So if we can exhibit a formulation that is amenable to algorithmic tools, then we can try to solve these sparse problems and come up with algorithms for them. Okay, so that's the end of my talk, and thank you.